Hello. Today we're talking about the NOR gate. So we just talked about the NAND gate recently, and we're going to go through a similar process with the NOR gate that we went through with the NAND gate. First, we're going to talk about what the NOR gate is, how we can use NOR gates to replace the AOI stuff like we did with NAND, how to implement an AOI logic circuit using only NOR gates. We'll just basically using the equivalents to substitute and simplify. And then we learned that switching to a single gate type, we're able to sometimes reduce the number of chips that are required to implement a circuit, thus making the circuit more profitable, cost less to build. So here is our NOR gate. So NOR stands for not or. So it's the opposite of an OR gate. If you remember an OR gate, the OR gate would put a 1 anytime you had a 1 at either X or Y at the input. Well, a NOR gate outputs the opposite. It's the opposite of an OR gate. It's saying this gate will put out a 1 only when neither of these is a 1. So here is the truth table. You only output a 1 when when both inputs are 0. If there's a 1 at either input, or if there's a 1 at both inputs, then it's going to return a 0. And then you can see that the gate is just an OR gate with an inverter bubble. So what happens is the X and Y go into the OR part of the gate and they get ORed together, so X or Y. And then the bubble goes over the top of both of them for the inverter. And then this just reminds us that, was it theorem 21, that you can break apart inverters like this and break the line, change the sign. So this is your NOR gate. So here's how we are going to use a NOR gate to make an inverter. It's similar to what we did with a NAND gate. We just put the same signal at both inputs of the NAND gate. Same thing here. We're putting the same signal at both inputs in our NOR gate. So the OR part just does X or X. But we have our Boolean theorems that tell us X or X is just X. So then we have X going through the inverter bubble, which outputs not X. So if we put X at both inputs of a NOR gate, that makes it an inverter. Next, we're going to look at how to make an OR gate using 2 NOR gates. So basically, we're going to use a NOR gate and then an inverter, right? And so since NOR is the opposite of OR, using an inverter after it will just make it OR. And then if you want to look at the signals, what's happening, you have X and Y going into this NOR gate. The OR part ORs them together, and the inverter bubble puts the inverter over both of them because it ORed first. Then we go into the inverter. Well, the inverter is just going to put another inverter on top of this. So then you have not X or Y, but the 2 inverters undo each other. So you just have X or Y. So that this NOR gate going into a NOR inverter, that is how we would that's what we would replace an OR gate with, using NOR gates. And then the last one is how do we replace an AND gate? So an AND gate, it's going to take 3 NOR gates. And what we do is the first 2 are wired as inverters for our 2 inputs. So then we'll have not X and not Y coming out of there. Then we go into the NOR gate. And then you can see what happens is you get The OR part will OR together the not X and not Y. And then the inverter bubble puts an inverter over the top of both. And now we can use our theorems. Theorem 21 is break this line, change that sign, and then the double negatives go away. So it's just X and Y. So we can replace any AND gates that we see with this little design. 2 inverters followed by a NOR. 2 NOR inverters followed by a regular NOR gate. So the next slide is going to be it's going to put those 3 equivalencies together. And this is a good chunk of information to have in your notes. I'm going to recommend that this ends up in your notes. Absolutely. The AND gate is 2 inverters that go into a NOR. The OR is just a NOR with an inverter. And the inverter is when you do the same input going to both inputs. So now we're going to look at an example, and we're going to start with the same circuit we did. We're going to use the same circuit we did when we were studying NAND gates. And this will be the process that we follow. So first we implement the AOI logic. So we're going to draw our circuit using AND or an inverter gate. Then we are going to replace all the AND or and inverter gates with the NOR equivalents, redraw that circuit. And then what we're looking for is any double inversions. So back-to-back inverters in line. Those cancel each other out, and then we redraw our final circuit. So here is part 1, where they've given us the circuit here. Here's the logic statement, B and not C, or A and C. So this AND right here is doing B and not C. This AND here is doing C and A. And then this ORs those together. So what we're going to do is we're going to take this inverter and we're going to replace it with a NOR equivalent, which is just the C signal going into both inputs of the NOR. The 2 AND gates, each one of those will be replaced by this little AND structure. 2 inverters that lead into a NOR. And then our OR gate will be replaced by a NOR followed by an inverter. So what that looks like is the following. We're going to just replace these across. So this was the inverter. That's just a NOR wired inverter. Then we had our 2 AND gates, which were just 2 NOR inverters that lead into a NOR gate. So there's one AND gate, and here's the other AND gate. And then they went into an OR gate. Here's the OR gate, which is a NOR going into an inverter. And then we can see right here that we have inline back-to-back inverters right here. So this signal right here, C is going to become not C, and then right here is going to become C again. So we can just take those both out and have C just go be C. So we are going to cross those guys out. And then what will happen is we won't have any inverters on this line here. So C is going to go straight over to here and straight down to here. So here we got C going straight over here. And then straight, this inverter was right here. So they moved these 3 inverters here that were down here. They just moved them up here. So now this circuit has 1, 2, 3, 4, 5, 6, 7 NOR gates. The original circuit had what, 4 gates? let's we could work through all of this. We can do that another time, but we can, it just proves that it's the same logic. But let's compare. This one had only 4 gates, and this one has 7 gates now. But since these are all the same gates, we actually end up using fewer integrated chips, because for this inverter, we need a whole chip, even though that chip has 6 inverters on it. For these 2 AND gates, we need a chip that has 4 AND gates on it. And for this OR gate, we need a chip that has this 4 OR gates on it. So we need 4 gates, but that would require 3 different integrated chips. But if we switch it all over to NOR logic, we have 8 gates now, so it'll take a little bit more wiring, but now you only have to buy 2 integrated chips instead of 3, so we can get the same functionality for a lower price by switching it over to NOR logic. Even though this one might be simpler to wire, this one will cost less money to implement.